The first part of question 1, it says differentiate with respect to x. Cool. So it tells us that y is equal to ln x squared plus 4 y is equal to ln x squared plus 4 minus x tan inverse x over 2. Nice and easy. All right, so this is y. So now we're asked to differentiate this, so we need to find dy dx. So we're going to differentiate it, and we're going to get dy dx is equal to, now when you're differentiating a log function, it's going to be, when you differentiate x squared plus 4, you get 2x. So that part is 2x over x squared plus 4. The differential of the denominator goes in the numerator. Then you're going to have to use product rule to differentiate this part. So it's going to be minus, using product rule, you keep the first, which is x, times the differential of the second. Now when you differentiate tan inverse, of x over 2, when you differentiate tan inverse function, remember that part is going to be 1 over the square root, 1 over 1 plus x over 2 square times the derivative of x over 2, and the derivative of x over 2 is a half. So that's how you differentiate that part. And let me not put this bracket here. Then it's going to be plus, keep the second, times the derivative of the first. So this is going to be dy by dx. So let us just go ahead and simplify this now. So dy by dx is working out to be 2x over x squared plus 4 minus, now this is how we simplify this, 1 times a half, 1 times a half, that's going to be 1 in the numerator, but then this 2 can go in the denominator. All right, so just to pretty it up, the 2 can go in the denominator to let it be, the x come in the numerator, so it becomes minus x over a half. 1 times a half, you can put the 2 in the denominator, so it's 2 times the 1 plus x squared over 2 minus tan inverse x over 2. You can simplify it some more if you want, you can, but that's not important. This is dy dx. You could simplify it further by, multiplying through by 2 to get x over 2 plus x squared. So instead of writing it this way, you could write, just showing you another way you can write it. Instead of saying dy by dx, I'm going to write y prime. You could write that y prime is equal to 2x over x squared plus 4 minus x over 2 plus x squared minus tan inverse x over 2. This is just an alternate way you could write it. All right, nice and easy. Now let's look at part 2 now. So for part 2, it is saying now, a curve is defined parametrically as x is equal to a cos cube t and y is equal to a sine cube t. Show that the tangent at the point P is the line y cos t plus x sine t is equal to a sine t cos t. So you have a point P, and P is the point xy, but they already give us what x and y are. This is the point P, all right? Now the equation of the tangent at the point P, remember equation of tangent is y minus yp is equal to the gradient of the tangent into x minus xp. So first things first, we need to find out what is this gradient of the tangent, all right? So in order to find the gradient of the tangent is dy by dx. That's the gradient of the tangent, dy by dx. But in this case, dy by dx is because it's parametric differentiation. Dy by dx is dy by dt times dt dx. Cool? Yeah, man. So this is going to be dy dx. So let us continue. So dy by dx is going to work out to be dy by dt. And remember up here it said that y is equal to a sine cube t. Y is a sine cube t. So to find out what is going to be dy by dt, it's going to be differentiate this, carry down the power to get 3a, subtract 1 from the power to get sine square t multiplied by the derivative of sine t, which is cosine t. So that's dy by dt. Then it's going to be divided by dx dt. Now remember what it said was x. So it said x was equal to a cos cube t. X is equal to a cos cube t. So to differentiate it, we carry down the power to get 3a. We subtract 1 from the power to get cos squared t times the derivative of cos. When you differentiate cos, you get minus sine. So it's minus 3a cos squared t sine t. So that's dy by dx. Now this 3a cancels out this 3a. All right, and I'm going to leave the rest for now. So of course, the equation of the tangent is going to be y minus yp. The y point is a sine cube t. Y minus a sine cube t. And that is equal to the gradient of the tangent. And the gradient of the tangent is given by this formula, which is minus sine square t cos t over cos squared t sine t. And then that is going to be multiplied by x minus xp, which is x minus x value is a cos cube t. So this is the equation of the tangent. Now, before we go even any further, as we can see, cos t is going to cancel out the square right here, and then sine t is going to cancel the square right here. So really and truly, we have minus sine t over cos t. So we can multiply through by cos t. We're going to multiply this equation by cos t. By multiplying by the cosine of t, what we're going to get is y times cos t is y cos t. Then multiply this by cos t, we're getting minus a cos t sine cube t. And that is equal to, now the minus sine t times x is minus, let me see, minus x sine t minus x sine t, and then minus sine t times this becomes plus a cos cube sine t. All right, so now the question that we may ask ourselves is, minus a cos cube sine t. Why is it freezing? Let me see what's going on. All right, it's back to normal. Good. So look at what we're trying to prove. Notice that there's no cube. Since there's no cube, then let's just group them together. We notice that we have a y cos t and an x sine t. So we're going to bring over this over here. Let me underline, we're going to bring this over to this side. All right. And then we're going to bring this over to that side. So let's do that and see what happens. Bringing over this, we're going to get y cos t bring over x sine t, so it becomes plus x sine t, and that's going to be equal to, we bring over a cos t sine cube t, so bring it over here, so it becomes a cos t sine cube t plus a cos cube t sine t. All right. So now all we need to do now is, as you realize you have a cos t and you have a sine t here, can factor out. So right now we're going to factor out. Let's factor out. Let's factor out cos t sine t. We're going to factor out cos t. Let's factor out a cos t sine t, because both of them have a in common. So we're going to factor out a cos t sine t. Factoring out a cos t sine t, we're going to left back with right here sine squared t. And factoring out a cos t sine t here, you're going to left back with plus cos squared t. So left back with cos squared t. But sine squared t plus cos squared t is 1. So you can throw away that part right here now. Let me underline it, sine squared t plus cos squared t. That's 1. All right, we know that. And so finally, all of this just works out to be a cos t sine t. A cos t sine t. And so hence y cos t plus x sine t is equal to that. Nice and easy. As we like to say, soft. Y cos t x sine t is equal to a cos t sine t. Soft with a capital T. So proven. Now we're finished with differentiation. It should be complex numbers now. Yes, let's go to complex numbers. Part B, complex number time. So part B says that determine the nature of the roots of the quadratic equation where the roots are alpha and beta. So you have x squared plus 3x plus 9. X squared plus 3x plus 9, and this is equal to 0. And they want us to determine the nature of the roots. To determine the nature of the roots, we use the discriminant b squared minus 4ac. So I like to call the discriminant d. The discriminant d is equal to 3 squared minus 4 times 1 times 9. And this is working out to be, let me just calculate this real quick. So I'm getting 3 squared minus 4 times 9. That is going to be 3 squared minus 4 times 9. That's negative 27. That's a discriminant, negative 27. Now, since the discriminant is negative, then we know that the roots are not real. Some people would say the roots are complex. So hence, the roots are imaginary, i.e. that is complex roots. All right, so these are complex roots. The roots are imaginary. Okay. It said express alpha and beta in the form re to the I theta, where r is the modulus and theta is the argument. So it says express alpha and beta in that form. So we need to find out what alpha and beta are. So let's find out what alpha and beta are. If we were to solve for the roots, we would get that x is equal to minus b, which is negative 3, plus or minus the square root of b squared minus 4ac, which we found already to be negative 27, over 2 times a, which is 2 times 1, which is 2. So x is working out to be minus 3 plus or minus the square root of negative 27. How can I break up this? The square root of, I know this can be broken up as the square root of 27. Look at that. That looks like 9 times the square root of 3 times the square root of negative 1 over 2. Yes, this looks like how to break it up. Then the square root of 9 is 3, and the square root of minus 1 is I. So it works out to be minus 3 plus or minus 3 root 3i. 3 root 3i over 2. All right, that's what I'm getting. So, of course, you can call one of the roots alpha. So alpha, maybe alpha is equal to minus 3 plus 3 root 3 over 2, 3 root 3i. And remember, both of them is divided by 2, so it's minus 3 over 2 plus 3 root 3 over 2i. That's alpha. And then beta is actually going to be minus 3 over 2 minus 3 root 3 over 2 times I. So that's alpha and beta. All right, nice and easy. So that's how we find alpha and beta. Now, of course, the question is nowhere near complete. It says we need to express it in the r cos form. So this is the answer in standard form, all right? But we need to express it in r cos form. So we need to find r. In this case, r is going to be equal to, r is minus 3 over 2 square plus root 3 over 2 all square. So this is going to give us r. And then we square root this result, of course. So let's square root this now. That will be, I want to put this in my calculator, minus 3 over 2. And I square that, I get 2¼ plus 3 root 3 divided by 2 square is 6¾ plus 2¼ I get 9, and the square root of 9 is 3. So r equals 3. If r is 3 for alpha, r is also 3 for beta. The only difference is that they're going to have different angles. All right, because if you're to sketch this, remember complex roots, they occur in conjugate pairs. All right, so they're going to be in different quadrants. So if this one is minus root 3 over 2 plus 3 root 3 over 2, this one is going to be x is negative over here, y is positive. So alpha is in the second quadrant, and then minus root 3, minus 3 over 2, minus 3 root 3 over 2i. This is when x is negative and y is negative. So that's in the third quadrant, that's where beta is. And so to find the angle with the positive x-axis, because that's what we want, in this quadrant, we have to remember it is pi plus. It is pi plus tan inverse. So this is pi plus tan inverse b over a. And in this quadrant, it's going to be tan inverse minus pi. All right, so let's go ahead and work out what the argument is. So the argument, we can call it theta, is equal to pi plus, so it's pi plus tan inverse, pi plus tan inverse of pi plus tan inverse b over a, which is 3 root 3 over 2, 3 root 3 over 2, divided by, instead of saying divided by, I'm going to write multiplied by minus 2 over 3. All right, so this 2 cancels this 2. This 3 cancels this 3. And so it's really tan inverse minus root 3, because this 3 cancels, so it's minus tan inverse root 3. So tan inverse of root 3, that's pi by 3. That's pi by 3. Tan inverse minus root 3 is minus pi by 3, and minus pi by 3 plus pi is 2 pi by 3. So this one works out to be 2 pi by 3. 2 pi over 3, which I could have probably guessed from just my sketch. As you can see, all of this is pi. This looks like 2 pi by 3. Based on my sketch, this angle come all the way around here looks like the same thing. This looks like 2 pi by 3 too, but let me find out. So I'll call this one theta 1. All right, I'll call that theta 1. Now let's find the angle in the second quadrant, theta 2. The angle in the second quadrant is going to be tan inverse of this minus pi. It's going to be tan inverse of this over this. Tan inverse of this over this is just tan inverse of this one over this one. Tan inverse of this over this. Minus over minus going to make it become positive. It's tan inverse of b over a. So it's just going to work out to be positive root 3, then minus pi. I'm positive that's what I get. So let's put that in our calculators now. tan inverse of root 3 minus pi. So I get minus 2 pi by 3 in the third quadrant, minus 2 pi by 3. So now I can finally put them in the R cost form. I can say that alpha is equal to R, which is 3 e to the I times theta. Theta for this one is 2 pi by 3. So it's 2 pi by 3i. That's alpha, 2 pi by 3i. And then I can tell them that beta is equal to 3e to the minus 2 pi by 3 I. That's beta. Nice and easy, soft. Now it says using De Moivre's theorem or otherwise, compute the value of alpha cube plus beta cube. Now it said using De Moivre's theorem or otherwise. Well, which one do we want to go with? Let's go with otherwise. Now alpha cube plus beta cube, if we remember back from unit 1 mathematics, alpha cube plus beta cube is equal to alpha plus beta all cube, alpha plus beta all cube minus 3 alpha beta into alpha plus beta. All right, this is how we find it using this right here. Not going to do De Moivre's theorem. That's kind of, don't want to get into that right now. So alpha cube plus beta cube is going to be alpha plus beta all cube. So it's going to be 3e 2 pi over 3 I plus and first and foremost, I don't even need to even use these values, right? We don't even need to use these values because guess what? Remember, this is the cubic equation, and what do we know about the quadratic equation? This is the quadratic, and what we know about quadratic, the sum of the roots alpha plus beta is minus b over a. So alpha plus beta here anyways is minus 3. We know this, and we know that alpha beta is equal to c over a. So alpha beta is 9. So we're done already. Like, we don't need to be working through so much complicated stuff about De Moivre's theorem. So alpha plus beta is just minus 3 cube minus 3 alpha beta is 9 times alpha plus beta, which is minus 3. So we work that out, and that will give us alpha cube plus beta cube. We don't need to do anything complicated. Minus 3 cube minus 3 times 9 times minus 3, and that's 54. So that's alpha cube plus beta cube. Of course, you could have actually used alpha plus beta, but I was thinking about it. I'm like, why would I want to add them in exponential form when that can be a little bit tricky sometimes? All right, so yeah, that's the reasoning behind of it. Then finally, the last part of the question, as it is asking us right now, it says, hence or otherwise, obtain a quadratic equation whose roots are alpha cube and beta cube. So now we know how to write the standard form of a quadratic equation. Now the new quadratic equation, if we recall from unit 1, new QE, new quadratic equation. Any quadratic equation is generally written in the form x squared minus the sum of the roots times x plus the product of their roots equal to 0. This is how we write a quadratic equation. So clearly, we're going to have to need to find the sum of the two roots and the product of the two roots. Now, the sum of the two roots is going to equal to alpha cubed plus beta cubed. So let's add that. So the sum is going to be equal to alpha cubed plus beta cubed. And alpha cubed plus beta cubed, as you can see, is 54. And then their product is going to be alpha beta all cube, alpha beta all cube, and the product of alpha beta all cube is going to be alpha times beta is what again? Alpha times beta is 9. So the product is going to be 9 cube. 9 cube is 729. And so the new quadratic equation is going to be x squared minus the sum of their roots, which is minus 54x, plus the product of their roots, which is 729. So plus 729, and that's equal to 0. So this takes care of question 1. Nice and easy, soft. Nice. On to question 2 now. Looking at question 2, it says fn of x is the integral of ln x to the n. So let's write that down. So it tells us that the integral of ln x raised to the nth power dx, they say that is equal to fn of x. So this is fn of x. All right, fn of x. So that's it, that's fn of x. This is fn of x. And so if you're integrating ln x to the n dx, what do? When you integrate this, what you're going to get is the integral of, you can rewrite ln x to the n as 1 times ln x to the n. And you might say, why did I put that 1 there? That 1 comes there because we're going to be able to use by parts by putting the 1 there, dx. Then now, when you have the 1 right here, you can remember by parts, you have to use the ILATE rule. So let me write down ILATE. And what does ILATE rule tell us? It tells us that we substitute for u. Logs come before algebra. And so we're going to substitute u as ln x to the n. And so du is going to be equal to, we carry down the power n, we subtract 1 from the power to get ln x to the n minus 1. Then we multiply it by the derivative of ln x, which is 1 over x. So it's really all of this over x. That's du. Then dv is equal to 1. And when we integrate 1, we get v is equal to x. So now we can continue now and say then that fn of x is actually going to be equal to, using by parts, it's uv minus the integral of v du. uv minus the integral of v du. So it's going to be equal to u times v and u times v, that's going to be x ln x raised to the n minus the integral of v du. Minus the integral of v du. Now x times this, the x is going to cancel each other, and then I'm going to factor out the n to have the integral of ln x to the n minus 1 dx. If you're wondering what happened to the x, let me put it in another color. Right here, you remember it's being divided by x, and then here it's being multiplied by x. But these two x will cancel each other in reality. All right. So what this works out to be then, it is just x ln x raised to the n minus n times, now the integral of ln x to the n minus 1, that's just fn minus 1 of x. That's how we do this question. Easily shown, soft. All right, nice and easy, soft. So we can write shown easily. Shown, too easy. Now it says hence or otherwise, show that f32 minus f31 is that right there. So that fnx, f32 minus f31 is that thing right there. So to do that, you have to start by writing down back that fnx is equal to x times, it is x times ln x to the n. Nice, it's x times ln x to the n minus n f n minus 1 of x. Nice. Now that we need to prove this, what are we going to do? Well, first thing I like to do is start by finding what is f3 of x. So to find what is f3 of x, we can substitute n as 3. So f3 of x will be equal to x ln x to the third power minus 3 times f2x, because 3 minus 1 is 2. 3 times f2x. Cool. All right, and so what we're getting is x ln x cubed minus 3 times f2x. And what is f2x? Well, f2x is we're going to replace again and with 2 now. So f2x is x times ln x square minus 2 times, replace with 2, it becomes 2 minus 1, which is f1 of x. All right, so before it looks any more complicated, I'm going to simplify what this is. So it's working out to be x ln x ln x ln x cube minus 3x ln x square, and then expanding, minus and minus become plus, it's become plus 6 times f1x. Now all we need to do is find out what is f1x. So let's do it, let's get it. Finding out what is f1x, it's going to work out to be x times ln x cube minus 3x ln x squared plus 6 times f1, and that's going to be 6 times f1 of x is going to be replaced with 1, and it's going to be x times ln x. So it's x ln x minus 1 times f naught of x. Now f naught of x, to find what is f naught of x, we have to go back and remember that f naught of x, when n is 0, ln x to the 0, anything to the 0 is 1, and so the integral of 1 is x. And so we can actually just replace this f naught x with just x. This is really x ln x minus x. And so this is the formula now for f3x. Good. Now that we have the formula for f3x, we can now evaluate what is f3 of 2 minus f3 of 1. All we're going to do is replace x with 2 and 1. So it's going to be f3 of 2, replacing x with 2. We're going to get 2 times ln x cube. Just want to make sure we make no mistake. Minus 3 times 2 is 6, so you get 6 times ln 2 square plus 6 times, in quotation or in open brackets, 2 ln 2 minus 2, close up that bracket, minus, now we're going to put in 1, but guys, we know that ln 1 is 0, so this is 0, this is 0, this is 0, this is 0, and so it works out to be 6 times minus 1, so it just works out to be, in bracket, 6 times minus 1, because everything else is 0, ln of 1 is 0. So all of this is going to work out to be 2 ln x cube minus 6 times ln 2 square plus, now 6 times 2 ln 2, that is going to be 6 times 2 is 12, so it's 12 ln 2 minus 6 times 2 is minus 12. Then this looks like minus, 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 minus. That becomes plus, so it's become plus 6. So finally, the final answer is just going to be 2 ln x cube, 2 ln x cube minus 6 times ln 2 square, 6 times ln 2 square plus 12 ln 2 then minus 12 plus 6 is just minus 6. Is that what they have? Let me check it. All right. Yes, that's what they have. That's what the question wanted us to prove. So finally, that's it. So we complete the proof. We can write soft. All right. So yes, that's it. Now part B now is partial fraction. All right. And integration. All right. So let's look at that. So this is the proof. So we complete it. So you can write soft. Nice. Part B. Part B is partial fraction, and in doing this partial fraction in part B, we have y squared plus 2y plus 1, and that's being divided by y to the 4 plus 2y squared plus 1. That's the question that we have. So first and foremost, we just need to know that, well, I can rewrite this as this is really y squared plus 2y plus 1 divided by, I can rewrite the denominator as y squared plus 1 all squared. I can rewrite this denominator because this is a perfect square. All right. Then by partial fraction, I know I can separate it as ay plus b over y squared plus 1 all squared plus cy plus d over y squared plus 1. I can separate it like that. So that is exactly what we're going to do. So to do that separation now, I don't know why the line came out like that. That wasn't how I intended it to be. I wanted a straight line. Let's give me a straight line. So finding the LCM now, yeah, this is it. So the LCM with these two is going to be, of course, y squared plus 1 all squared and this into this just leaves ay plus b then plus all of a sudden the writing is so much smaller. Then this into this is going to leave cy plus d being multiplied by y squared plus 1. And all of this is, of course, equal to this over here. So it's equal to your y squared plus 2y plus 1 over your y to the 4 plus 2y squared plus 1. Now, what did we learn in primary school? We learned in primary and preparatory school that whenever the denominator are the same, we equate the numerators. So we're going to equate the numerators, so that implies that equating numerators, y squared plus 2y plus 1, that's going to be equal to ay plus b plus, now if I were to expand this, I will get cy times y squared, which is plus cy squared, plus cy times 1 is plus cy, plus dy squared, plus d. Nice and easy. Now, what we can do now is equate coefficients. Notice that we have cy times y to give us cy cubed, not cy squared, cy cubed. Cy times y squared is cy cubed, cy times 1 is cy, d times y squared is dy squared, d times 1 is d. Notice right here that we have a cy cubed, and there's no y cubed term over here, and so c must equal 0. C must be 0. all right? And let's go to blue now. We have a y square here, and we have dy square here. And so the coefficient of this is 1, and so d must equal 1. All right? D must equal 1. Now that we get that d equal 1, let me see. All right, so we need to find A and we need to find B. Let's equate now y terms. Equating y terms, we have 2y here, and we have ay plus cy. So what that is telling us then is that 2 is equal to a plus c. But c is 0. Remember, c is 0. And so c is 0. And so since c is equal to 0, it tells us that a must be 2. A equal 2. Nice. So now we'll find a. Finally, let's go ahead now and find out our constant. We have 1 here is equal to b plus d. So 1 is equal to b plus d. But we already know what is d. D is 1. And so b must equal 0. So b must be equal to 0. Because 1 is equal to b plus d. All right, now that we get that, then we can replace these now. So just for shortening, I can't bother to write out all of this again. Let me call all of this fraction I, right? I'm calling the fraction I. So therefore, the fraction I is equal to ay plus b. Ay plus b, what is y? A is 2. So it's equal to ay, which is 2y over y squared plus 1 all square all right, plus cy plus d. C is 0, so it's d now. D is 1 over y squared plus 1. Nice and easy. Soft. And this is it, so prove it. Remember, addition is commutative, so you can refix the order to give them what they had. Nice. Then it says, hence, evaluate an integral. So hence, so part 2 says hence evaluate the integral from 0 to 1 of y squared plus 2y plus 1. Hence, evaluate the integral of y squared plus 2y plus 1 over y to the 4 plus 2y squared plus 1 dy. Hence, evaluate this integral. So to evaluate this integral, what we're going to get is that this is actually equal to the integral from 0 to 1 of, we just showed that y squared plus 2y plus 1 over that was the same as 1 over y squared plus 1. So it's going to be the integral of this dy plus the integral from 0 to 1 of 2y over y squared plus 1 all square. So let's go ahead and knock out this integration. Now to do this integration, 1 over y squared plus 1, when you integrate that, it's going to be tan inverse of y. This is just tan inverse of y from 0 to 1. tan inverse of y from 0 to 1. Plus, now right here now, let's do the rest, this integration here. Now if we were to call u, let's call u y squared. If we were to call u y squared plus 1, right here, if we were to call this u is y squared plus 1, then I would realize that du would be 2y dy. All right, so what I'm going to do then is I'm going to rewrite this as the integral from 0 to 1 of 1. And then I'd have to change the limits of the integral because I'm saying that u is y squared plus 1. So when y is 0, then the lower limit becomes 1. And when y is 1, upper limit becomes 2. So it's now the integral from 1 to 2 of 2y dy is du, so it becomes 1 over, this becomes y squared plus 1 is u, it becomes 1 over u squared du, and I'm integrating from 1 to 2 using substitution. Plugging in 1, I get tan inverse of 1. So I get tan inverse of 1 minus tan inverse of 0, which is minus 0, plus, when I'm doing this integration now, it becomes, this is really u to the minus 2, so I add 1 to the power to get u to the minus 1, divide by the power of minus 1, and of course I'm integrating from 1 to 2. Integrating from 1 to 2. So let's go ahead and do that. Tan inverse of 1 is, I don't know, so I put it in my calculator. Tan inverse of 1, that looks like pi by 4. That's pi by 4. Plus, we put in 2 and 1 now. When we put in 2, we have 2 to the minus 1. 2 raised to the minus 1 divided by minus 1 is minus a half. When we plug in 2 here, 2 to the minus 1 divided by minus 1. That's minus a half. Minus, when we put in 1 here, it's going to be 1 raised to the minus 1 divided by minus 1. 1 raised to the minus 1 divided by minus 1 is just minus 1, so it becomes minus a half plus 1. Minus a half plus 1 is just minus a half plus 1 is just a half. So the final answer is just pi by 4 plus a half. Nice and easy, that's the answer. Just to be safe, let's check it. Just to be safe, we're just checking it right here. All right, just being safe. Plug in back 2 again, 2 to the minus 1 over minus 1. Minus 1 to the minus 1 is 1 divided by minus 1. Yes, it's a half, so this is right. So that takes care of module 1. Let's go to module 2. Module 2, question 3.